This week we're going to be looking more at kinematics, and we're going to finally start getting some of our kinematic equations that we can use to start solving some problems. So let me just remind you, when we say kinematics, we're talking about the mathematical relationship between the position, the velocity, and the acceleration of an object. And hopefully you've seen this a little bit in your calculus class. So for those of you that really remember calculus, a lot of this might be review. For those of you who don't remember calculus, that's totally awesome because I'm here to teach it to you. Okay, let's just start with a little thing to think about that's kind of a review from last week. So press pause, take some time to read through this and really see if you can pinpoint this difference, because that's going to help you deal with these different terms that we're talking about here. So press pause, think about it, and when you think you have an answer, press play again. Okay, so the real key here is that total distance traveled and displacement are the same if the object only moves in one direction. Remember, when you're walking on that number line, if you just move in one direction, no matter what, your displacement is the same as your total distance traveled. It's only when you change direction, if you turn around at some point, that's when your total distance traveled is different than your displacement. Because remember, displacement only cares about where did you start and where did you end. So I think a really nice thing to remember is like running around a track, right? When you run around a track, you make a complete circle. You start and end in the same spot. Your displacement is 0, but your total distance traveled is definitely not 0. So if an object only moves in one direction, the total distance traveled is the same as the displacement. And the average speed, that's the one we're used to thinking about, how fast something's going, is equal to the average velocity. Remember, velocity and speed are related, but velocity takes into account direction. If your object doesn't change direction, these two things are the same. If an object turns around or changes direction at all, now the total distance traveled will not be the same as the displacement, and the average speed will not be the same as the average velocity. So we're going to keep building on this idea, but I want you to try to keep these things separate in your mind. Remember, the things that make sense to you, the things that you care about in your daily life, would be the total distance traveled and the average speed. The thing that matters in physics class that doesn't make sense yet is displacement and average velocity. So I really want to keep coming back to these ideas to help you keep them separate. Okay, let's try to put together two concepts. So here we have some position versus time graphs showing the position of an object at different points in time. And I want you to try to make sense of this motion by drawing a motion diagram. And very specifically, include the coordinate system, like where the x equals 0 is. Here's x equals 0 in all these graphs. So try to draw a coordinate system with like a basically a number line, and then try to draw a motion diagram that goes with it. So press pause, take some time to work through this, and then we'll go through it together. Let's look at the first one. So the first one, the object starts at the position of x equals 0 on our number line. So there's that first position. And the object is moving in the positive x direction. So I'm showing it moving to the right. How do I know it's moving in the positive x direction? Because this is x values getting bigger and bigger. And here I have the x values going bigger and bigger in this direction because I'm drawing the x axis horizontally. And the other thing I'm going to show is that I can tell this object is moving at a constant velocity. How do I know it's moving at a constant velocity? Because over each time interval, the object, over this much time, the object moves the exact same distance in the x direction. Each time interval, the distance moved in the x direction is the same. So that's what I'm showing here. All of these velocity arrows are equal in length, meaning this is all the same speed. And I'm saying there's no acceleration. That's what the 0 here means. For this graph, it's pretty much very similar to this. The object is still moving in the positive x direction. The only difference is now they started at a negative x position, and then they cross that x equals 0 sometime later. That's over here. For this graph, we're going to start at a positive x position. We're going to move in the negative x direction, again at a constant velocity because this is a nice straight line here. And I'm going to cross the origin and then eventually have a negative x position, so something like this. Here's where I cross the origin. And over here, I want to start at the origin and then move in the negative x direction at a constant velocity. Again, I'm making all the arrows the same size because I have a nice constant velocity here It's the x position is changing at the same rate. I can tell by this straight line here. Now, if this was tricky for you, that's cool. Press pause, rewind, watch this part again. Watch it a few times. Go back and review motion diagrams. Keep watching this little section until it makes sense. Okay, this is how we make sense of kind of the physics concepts before we even get to our equations. So all of those graphs were examples of what we call uniform motion, and that's going to be the first type of motion that we talk about. Here was our definition of average velocity that we worked with last week. And something interesting happens if you remember those graphs I just showed you. We had plotted x on the vertical axis and time on the horizontal axis. So this part right here sure looks an awful lot like the slope of that graph, because this was on the vertical axis, this was on the horizontal axis. This is the change. This is like rise over run, which is the slope of our graph. So that means the average velocity is given by the slope of this graph. So here is a graph that is a very specific type of motion called uniform motion. All of the graphs we just saw were examples of uniform motion. And the key here to define what uniform motion means is that uniform motion is when an object travels with a constant velocity. Okay, the graph of a uniform motion is a straight line. The position, the x versus t graph, the position versus time graph, is a straight line. That's the key for uniform motion. Another way to think about it is we could say the object doesn't slow down, it doesn't speed up, it's just traveling at that constant velocity. It doesn't turn around, it's just maintaining a constant velocity. The acceleration is zero, it has a constant velocity. All of those things I just said are properties of uniform motion, but I think this is kind of the simplest definition here. Real quick, let's just look at a different type of graph. So here's the x versus t graph with some different positions marked out. This is not uniform motion. It's not uniform motion because at a certain time interval, like from this time to this time, we only move this much in x, and from this time to this time we've moved a lot more in x. So I would describe this object as speeding up. It's going faster and faster. This is not uniform motion. The graph, the slope here, is not constant. That means the velocity is not constant. Remember, the velocity is the slope. Here I have a nice constant slope. That means a constant velocity. That means uniform motion. Here my slope of my graph is changing. And since the slope is my velocity is not constant. If my velocity is not constant, this is not uniform motion. Later, we're going to come back and deal with this type of motion. But for now, I want to focus on uniform motion. So let's get ourselves our first equation. You might think this is an equation. Yeah, but let's just rearrange it a little bit. What I'm going to do is just ignore this middle piece for a second, and I'm just going to multiply both sides by delta t. And that gives me this form of an equation. Okay, so this is a way that we can calculate if you know the initial position of an object, you know its velocity, and you know how long it's traveling with that velocity. This will let you calculate the final position of the object. This equation is not that surprising. You probably could have figured this out on your own. Okay, so this equation is useful in this form, but I'm going to write it using the delta x. Okay. So let's just remember for a second, what is delta x? Delta x is displacement. It's that new variable. It's just the change in our position, x final minus x initial. So these two equations are exactly the same. It's just here we're writing it in terms of delta x as a single variable. We've combined x final minus x initial into one single variable. Why do we do that? Because that's what really ultimately matters as we move forward and look at our kinematic relationships. It's the displacement that matters. From that, we can figure out x initial or x final. But really, I want to think of this as one single quantity. So this is the form of the equation I'm going to focus on the most. So just remember, delta x is our displacement, v is our velocity, delta t is our change in time, and I like to write, when I write my equation in my notes, I like to write these words here just to remind myself what the variables mean, because maybe in a few weeks when it's time to take a quiz, you're not going to remember what those variables are. It's just nice. And I also like to, every time I write down displacement in the beginning, I like to really remind myself, what is displacement? Oh yeah, change in position, x final minus x initial. Let me just emphasize which now, but I'm going to do it a lot. This equation only works for uniform motion. It only works when the velocity is constant. It only works when the acceleration is zero. If it's not uniform motion, we're going to have 4 different equations to replace this one. Okay, so uniform motion is very simple. Constant velocity, no acceleration, no changing direction, no speeding up, no slowing down. This equation only works in that case.